Welcome to AP Chemistry at High School. I'm BBrown, and today we'll be finishing section 8.5 and going through part of section 8.7. Now we're going to start where we picked off with yesterday, which is looking at drawing Lewis dot structures. Now, one of the problems that arose with Lewis dot structures is that there are some instances where there were actually several different Lewis dot structures that would all obey the octet rule. We're not talking about resonance. We'll get in that in a second. That's going to come after we get into formal charge here. So let's say, like the case of the carbon dioxide here, we've got really two valid ways by octet rule of drawing this. Both of these fit the octet rule. So how do we know which one is correct? So there are instances where there are multiple ways of drawing the same thing. They all fit the octet rule. So how do we tell which one is how this is actually reflected in everyday life? Well, one part of this is dealing with bond length here. One of the ideas that you should remember from pre-AP chemistry is that single bonds are longer than double bonds, which are longer than triple bonds. So when we look at these two structures in the real world and do experimentation, if this was the correct structure, we should see a lopsided molecule. This half of the molecule would be significantly shorter than the other half is. Whereas these are both double bonds, you would see the exact same bond length in each. So we could rely on experimental evidence to tell us that, oh, it looks like this way of drawing CO2 is actually the right one with two double bonds on each side. Well, you can't do experimentation with everything to see, what reality basically dictates is the best way to do something. So how do we actually determine which one is the right one? Well, what we use is a process known as formal charge. Now, this has limited use. So really the only way we ever really use formal charge is when we have a question about, okay, which one of these is right? These are two different ways students have come up with how to draw this thing. Who is correct? Well, formal charge is a way to kind of figure out who is correct. Now, to assign formal charge, the first thing you do is you count the number of valence electrons around the atom. So in the case of our CO2 drawings down here, in the case of oxygen, it's always going to have 6. So notice every instance of oxygen here we have a 6. Carbon, we always have a 4. So the first thing you do is basically figure out, okay, for that atom, how many valence electrons do we have? Then you look at the picture. Add the number of unshared electrons to half the number of the shared electrons. Because remember, in a bond, in essence, you can think of it as each one is contributing 1. Now, that doesn't always happen, but it's an easy way to look at the picture here. So in the case of our drawings, this would imply that the oxygen has 1, 2, 3, 4, and then half of a double bond. Well, each bond it has half of, so that's going to give us 1 there and 1 there. That's a total of 6. Whereas in the case of our carbon, we have, 2 double bonds. Well, carbon is going to get, in essence, half from each bond. So what's around the carbon? We would say that the carbon has 4 dots there. So that's how you do the next part. So first is how many valence electrons you've got. And then second, by the picture, every unshared electron is 1 electron. Every bond is a half of that. So instead of 2, the bond is split equally between, and each one basically gets 1 in the bond. So you go through and you evaluate your structure using those ideas. So first, how many valence electrons? And then second, based on the picture, how many do you see? So in this far oxygen right here, I've got 1, 2, 3, 4, 5, 6, and then half that bond, that's going to be 7. So I put a 7. The carbon, 1 for here, and then 1 for each other bond, that's 4. And then my oxygen, 1, 2, 3, 4, 5. So 5. So that's the next thing you do, is add up the number of unshared electrons with half of your shared electrons. And then subtract this value from the number of valence electrons. So then you go and subtract. So find valence, find out in essence around each atom about how many electrons do I really have in the picture, and then subtract the 2. Now, the way formal charge works is the best Lewis structure is always going to be the one with the fewest charges. You end up with a more stable, lower energy situation if you have lower formal charge here. So in essence, this one, by that criteria, would be the better way to draw CO2 because it has a lower formal charge. So this one is going to be the stable form of carbon dioxide. The other one is just not a stable way to write it. Because really what you're implying is, effectively, this oxygen is -1 in charge, and this oxygen is +1 in charge. Well, they're both oxygens. So a better way to draw this would be with the one with fewest formal charge. So when we look at these three pictures down here, now the very first one here, so ion A and how it's drawn. Well, when you look at formal charge, you're going to end up with these numbers. Now, as a quick review of what we did, so let's run through it. Nitrogen, looking at the periodic table, based on where it's at, nitrogen has 5 valence electrons. So this has got 5, this has got 4, and this has got 6. And then we count it up. 1, 2, 3, 4, 5, 6, and then half the bond, that makes 7. So when I subtract, I get -2. Next one, my carbon. Well, carbon has 4 valence, 1, 2, 3, 4. 4 minus 4 is 0. And then my oxygen, 1, 2, 3, 4, 5. 6 minus 5, +1. So if I look at all of my substances here and do that same exact thing for all of them, these are my formal charges. So this was a -2, 0, +1. The middle one is a -1, 0, 0, and the far one is a 0, 0, -1. So first criteria, you want the one with the fewest formal charge. Well, based on that criteria, we can get rid of that one. That's got a higher overall formal charge, so that's less likely to be valid or stable. So by that criteria, we're going to throw out the first one. Well, I'm still left with 2. So how do I know which of these two is a better way to draw it? Well, the second criteria, remember, a strongly electronegative atom is more likely to get a share of the electron. So in other words, it's more likely to have picked up electron and be looked at as a -1 compared to its neutral atom. So the best Lewis structure is going to be the one with the fewest formal charge, as well as the one that puts negative charges on the most electronegative. Well, when you look at where nitrogen and oxygen are at on the periodic table, because it's about the N and O, because the carbon is 0 in both of these. Well, remember, electronegativity increases when you go to the right and increases when you go up. Well, they're in the same period and oxygen's farther to the right. So oxygen is my more electronegative substance. So if something is going to have a formal charge of -1, it really should be the oxygen. So by that second criteria, this is going to be my best way to represent. So formal charge, 2 criteria is basically. 1, lower formal charge is more stable. And 2, if you really evaluate where you've placed charge, it should always be on the more electronegative element. And those 2 things basically are the 2 criteria to use. Now, you don't use this a ton. It's just I've got 2 pictures, or I drew 1 picture, the person next to me drew 1 picture. When we look at what each person did, we both followed the rules and we both have we followed octet rule. So who's right? Well, formal charge is a way to determine who is more likely to be right. Now, next idea is in 8.6. This is resonance. So if we want to draw Lewis-Strauss structures, sometimes we have a situation where we have more than one way to basically represent the exact same thing. So this is a Lewis-Strauss structure that we would draw for ozone. The problem is this is at odds with what we know to be true, which is the observed structure of ozone. Now, if we have both O to O single bonds, they would be the same length. And both of the outer oxygens would have a charge of -1/2. That's what we see to be true with this situation. So we should have equal bond length, because that's exactly what ozone looks like. And we shouldn't have, 1/2 being a 0 and the other half being a -1 in formal charge. If we did the formal charge, it should really be distributed evenly and equally in both cases. So both outer oxygens would have an effective charge of -1/2. So it's like they each got part of an electron. So one Lewis structure really can't depict that. I mean, we could draw this structure here, and that's got a double bond with a single bond. Well, this oxygen to oxygen is for all intents and purposes the same as that oxygen to oxygen. So what we really have is, sometimes it's like this and sometimes it's like that. In fact, it's like each of them. So it's like both of them at the same time. So what resonance really is when we have multiple pictures of the same thing and they all appear to be partially correct. So it's kind of like a bond and a half here and a bond and a half here. If I had 1.5 bonds in each places, that would be a non-lopsided equal distant molecule. And that's exactly what we predict. It looks like it's shorter than a single bond, but longer than a double bond. It's like it's a bond and a half at each position. So resonance is really when we have an equal choice about where to put a multiple bond. And the reality is, in the real world, it looks like it's in all positions partially at the same time. Well, one resonant structure can't accurately depict that. So we had to draw two, and we would connect them with a double arrow. So just as green is a synthesis of blue and yellow, ozone is really a synthesis of these two resonant structures. Both together would really make our ozone molecule. So what we do is, for resonance, we would draw one and then just draw the other and connect them with a double arrow. So it looks like it's partially both of those at the same time. So one of the problems with Lewis structures was it didn't really accurately allow us to talk about these kind of situations. So resonance is basically an alteration slightly of original Lewis theory to come up with a more accurate description. So anytime you have an equal choice about where to put a double bonds, you're going to have resonance. So in truth, the electrons from, in this particular case, so this is another substance where we have an equal choice about where to put our double bond. Um, what really happens is it looks like it's partially in both positions. So really, these electrons are not localized in this bond or in that bond. Those electrons are shared equally between the two. So it looks really more accurately like this. And then that double bond is kind of shared between the two substances. So they're not localized to one bond or the other. They're in both positions, so they're delocalized. So one new thing from last year to this year, because you looked at resonance last year, when you looked at, when you have an equal choice about where to put a multiple bond, you have resonance. So it looks like it's partially in each position. Well, what it really means on a fundamental level is that those electrons involved in that bonding are delocalized between the two positions. So they're not stuck between one carbon to oxygen bond or the other. They're delocalized between each. So in essence, it looks like each one is a bond and a half. And that's exactly what experimental evidence shows us is true between the two. Now, organic compounds like benzene also display resonance. And benzene is a really important organic compound. It's used in tons and tons and tons of different things. So benzene is basically a 6-carbon ring with alternating double bonds. Well, if you take a look at it, I could draw the double bonds here and here and there, or I could draw them in these positions. Well, the reality is it looks like it's delocalized in all those positions. So once again, this is a double bond, single bond sharing situation. So really, this would be a way to show that delocalized nature of the bond that occurs in something like benzene. So in this ring, the resonance actually, the delocalized nature of that extra bond that could be in different positions is delocalized throughout the entire ring. And as far as bond length measures out, each C to C bond looks like it's about 1.5 bond order or bond length. So it's delocalized throughout the entire ring in the case of benzene. So it's commonly depicted for benzene to just draw a circle inside it to signify that delocalized nature of the electrons in resonance. So as far as what you're doing, do the exact same thing you did last year. When you have a choice about where to put it, you would draw it in each position and connect them with the double arrows. Technically, that would be the best way to show what you've got. But you need to understand a level deeper. Those electrons that are involved in resonance are delocalized throughout all of those positions in resonance. Now, back to our benzene as a really common thing. What do every one of these substances share in common? And we're going from aspirin all the way to mothballs. Well, if you actually look at their picture, you can see that delocalized benzene C6 ring in each and every one of those molecules. So that is called an aromatic ring, and it's a really common component to many organic molecules. So if you have any pharmaceutical you're taking for some medical condition, I bet if you really looked at the chemical Lewis dot structure of the substance, you would see somewhere in there it's probably got one of these delocalized benzene rings. Um, one of the things we'll get into later when we get into structures, you'll see that these end up flat in nature, and we'll get into hybridization next. But one thing we have already talked about is really all the C to C's in this ring are going to be equal in length. So that's a really, really versatile molecule, is the delocalized nature of the benzene ring that pops up in just a ton of different commercially available and useful molecules. Another example of this is actually this substance. Toluene is the benzene ring with a CH3. So right here I've got my toluene. And notice I've got three of these groups substituted on it. Those are nitrogen groups. I've got three of them. That would be tri. Well, this is actually TNT. So trinitrotoluene, or TNT, an easier way to basically say what this molecule is another nature of our resonance structure of benzene in a substance. This just happens to be highly, highly unstable. In TNT, it's useful for explosives because it's so incredibly unstable at very high temperatures, so above 450 degrees Fahrenheit, or if you just shock it, so you shake it really hard, in its pure form, it's highly unstable. It can literally cause it to decompose at that point, releasing tons of energy. And that actual substance, the trinitrogen toluene, it's actually an intermediate in a lot of different chemical things. So you see this benzene ring popping up all over the place. So that's one aside about resonance that your book gets into just a tiny little bit. Now, the next section, 8.7, we're going to just scratch the surface of this. So we'll end up finishing this in our next set of notes. But right now, we're going to look at some exceptions to the octet rule. Now, there's actually three different types of ions or molecules that don't follow the octet rule. I want to make sure you have an understanding of each. And one of the things that's helpful with this is if you've got your book open, because they've got nice pictures to refer back to. So one of the things that's often useful is being on page 322 and 323, where you see these different exceptions to the octet rule. So that way, if you're not sure about something that I'm talking about, you've got a quick reference to look at. Now, the first one we're going to look at here is a relatively small group. So between the exceptions, this is the least important. This is something that is less likely to be on one of my tests here on the AP test because it's relatively rare and usually quite unstable and reactive. So typically, if we've got it, it's going to react with something else to make some new compound. But there are ions that actually have an odd number of valence electrons. Highly unlikely and usually unstable, but technically possible. Examples of that would be nitrogen monoxide and nitrogen dioxide. Technically, when you look at the actual structure, we would expect to see, based upon experimental evidence, it would appear like we have an unshared pair of electrons in it. This is going back to that whole paramagnetic, diamagnetic. We have an unpaired electron here. So this would be weakly attracted to a magnetic field. And the single electron would be an example to show that. Now, between these two ways of showing this substance, which one would be better? So if I couldn't remember, I just remembered NO as an example of an odd octet situation. Well, remember, formal charge is how we often tell when we're not sure between two different structures. So if we look at assigned formal charge, the way it would work out is this one is going to have our negative charge on our more electronegative substance, the oxygen. Because remember, oxygen has 6 valence electrons, and what we've got is 1, 2, 3, 4, 5, 6. That's going to give us a 0 situation. Nitrogen is 5. If we count out here, we've got 1, 2, 3, 4, 5. So by formal charge, which is lower formal charge, or the second criteria, if lower, but they're both lower in formal charge, and we can't decide which one places the negative charge on the less or the more electronegative thing. In this particular case, you can see that one's 0, 0. But when I do this one, so they're 5 and 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. That would give a +1 for this and a -1 for that. This is going to be negative if there's at all negative, and that's higher formal charge than this. So by formal charge, it would allow us to say, hey, that's probably the more likely substance. So quick review of formal charge again. So if you remembered, NO was a substance that's an odd octet situation, but you couldn't remember what it looked like, that would be one way to figure it out. Oh, let me get rid of all this garbage. So if you actually draw a accurate depiction of what's happening with NO2, you would see this gives you a situation where we have actually resonance between our two oxygens here. So this is a resonance and odd octet situation in NO2. But keep in mind, while this does exist, it's relatively unstable, very rare, and unlikely to pop up on the AP test or my test. What's more likely to appear is the other situations the book talks about. When you have less than an octet, I'm going to call it a deficit octet, so it's less than 8. And when you have more than an octet, an expanded octet. Now, hydrogen is the one that we've already talked about. Remember, hydrogen only has 2 electrons, 1 bond, and it's done. But all the elements that are very small can do this. So things like beryllium and boron, they're also very small atoms. It's unlikely for them to get a full octet and become stable. So beryllium ends up with something that forms two bonds and has no unshared pairs and is still stable. And boron will form three bonds, three single bonds, and will have no unshared pairs on the boron, but yet it's still stable. So these are three common deficit octet situations. Now your book gets into the concept of BF3. So let's say I have somebody who tries to draw BF3 and they say, okay, it looks to me like it's a resonance structure because I'm going to make that boron have a full octet. So that means I'm going to pull a pair of unshared electrons from a fluorine and make a double bond. And since I have an equal choice about where to put it, it's going to be resonance for BF3. So if somebody tries to force the octet rule, then rather than realizing it's a deficit octet and says, okay, this is what we've got. Well, keep in mind, what's going to happen here is it's going to give um, boron, a filled octet is going to basically make the boron negative in charge, and it's going to face or cause one of the fluorines to be a positive one in charge. Well, this can't be an accurate depiction for the electron distribution based upon what we've talked about. I mean, fluorine is highly, highly electronegative. It's never going to form a +1 biformal charge. That's just unlikely to happen. So this would not be an accurate way to do it. So what's a better way to do it? Well, just making an exception to the octet rule. If you evaluate this by formal charge and look at the picture, this one is going to give you a much more stable, low formal charge situation without positives on the fluorines. So if given a choice between drawing by the octet rule and making it work, or drawing it as a deficit octet, by formal charge considerations, this is going to be a much better way to do this. So the structure with double bond between a boron and fluorine is just much less likely to be favorable and stable compared to the other. So the lesson is, if filling an octet of a central atom results in a negative charge on the central atom and a positive charge on a more electronegative outer atom, then don't fill the octet. That's the way your book puts this. So in the case of something like BF3 or BCl3 or BH3 or whatever, putting a double bond there just doesn't make any sense. So don't do it. Now, that's the way the book explains it. Honestly, the easiest way to do this is if you see Be, two single bonds, no unshared pairs. If you see boron, three single bond, no unshared pairs. Yes, you could talk about formal charge and if you tried to make octets in each of these and what that would mean. The reality is, just know, beryllium is going to form two single bonds and no unshared pair. Boron is going to form three single bonds and no unshared pair. That's the much faster way to do it, rather than worrying about formal charge and everything else. Expanded octets. This is probably the largest class of exceptions because it happens with a lot of different substances. And it's really one of the ones that's easiest to see because it kind of stands out. PCl5, you have to have 5 chlorines stuck to the phosphorus. The only way that can happen is if phosphorus has an expanded octets. So these tend to stand out and they're more common exceptions. So beryllium boron, you should know those. Those are deficit octets. And expanded octets you should also know. Now, atom, what's really happening inside here is when you have an atom from the third period, and below on the periodic table, so third period, fourth period, and so on, they can accommodate an expanded octet for a variety of reasons. One of which is there's a nearby D sublevel that has space available for bonding. So we can end up forming a hybridization with a D sublevel because it's so close and it's unfilled. So in the case of phosphorus, we have a nearby 3D that doesn't have any electrons in it. So that gives us basically the room for having additional electrons in there. So you'll see this typically in period 3 on the far right-hand side of the periodic table and below. So something like phosphorus, something like arsenic, and so forth. Now, size can also play a role. The larger the central atom, the more likely it is to do this. And that's because bigger things have minimal electron to electron repulsion. And size of the outer atom can also play a role, and that deals with electron-electron repulsion as well. But the long and short of it, the only way that PCl5 can make a valid substance is if we have 10 electrons around the phosphorus. So it's allowed to expand, and we end up with an expanded octet. Not 4 unstable, 4 single bonds, but in this case, 5 single bonds. So not 8, but 10. And what's really happening is we're getting our d orbitals involved in bonding. Now, once again, your book goes through a discussion of this idea. So even though we could draw a Lewis dot structure for the phosphate, so this is a typical substance that has phosphorus in it and oxygen, that could potentially be an expanded octet type situation. So we could draw it and follow the octet rule, and we would get something like this. We could also get it try and draw it and not follow the octet rule, and we get something like that. Well, between these two, you'll notice the formal charge has been done. Which one gives us a better formal charge arrangement? Well, the one with the double bond than it does. So this eliminates the charge on the phosphorus and one of the oxygens, and we end up with a lower formal charge situation. So it's going to end up being more stable. So this would be a better way to write the phosphate anion. And I know it doesn't follow the octet rule, but phosphorus is one of those substances that often does this. So the book says what the lesson is when the central atom is on the third row or below and expanding the octet eliminates some formal charge, then do so. Well, honestly, you're unlikely to be asked this on the AP test. Well, you could, I guess, and formal charge would be the way you tell it apart and explain why that's the better way to do it. Typically, it's going to be something that's very loud. If you see something like SF6, you know it's going to be an expanded octet. So there's the book way to do this, and there's the easy way to do this. When you see more than 4 on the center, it's an expanded octet. When you see you have beryllium or boron, it's going to be a deficit octet. And that basically ends our second set of notes over the chapter, our third set of notes over the chapter.